In sections 4.1 and 4.2, we talked about how to graph quadratic functions. When we go into solving quadratic equations, one of the biggest tools that we can use to help solve quadratic equations is by factoring. Now, the idea of factoring a quadratic equation or a quadratic expression comes from the FOIL method. So, for example, if I have two binomials, x, like something x plus this, something x plus that, if I wanted to expand this to get it into standard form, normally I would FOIL, where I would do first, outside, inside, last. And then I'd combine like terms, specifically the inside and outside terms, and the standard form will be complete. So when we factor, we want to try to think of doing the process as doing this in reverse, okay? The thing is, however, before we do this, we have to check to see if all the terms have common factors. Like sometimes you have a quadratic function where all three terms are divisible by the same number. By taking out that number, it'll make our factoring a whole lot easier. Let me show you an example here. So let's say that I have a quadratic function like this. Here it is. 4x squared plus 20x minus 56. Well, obviously, 4, 20, and 56 are all divisible by 4, so I can factor out the 4. So I have x squared here since I took the 4 out, which technically there's a 1 here because anytime you factor, it's kind of like you're dividing. 20 divided by 4 is 5. 56 divided by 4 is, let's see, it's 14, minus 14. Okay, so you definitely want to check to see if each term has a common factor before you continue to factor. But there are two. I'm gonna come back to this example in just a minute. But there are basically two main cases where we factor quadratic functions in standard form. One of them is when a is 1 or negative 1, and when a is anything else but that. And of course, remember a cannot be 0. If my value of a is 1 or negative 1, then we can just use what's called the AC method. So the AC method is called that because it involves a times c. So first things first, if your a is negative 1, definitely factor out negative 1. The reason for that being that if your a is negative, then it might mess up your factoring. So you always want a to be positive, okay? Then you want to multiply a times c and identify all the factors of that number, whatever that number is. Then we need to pick a pair of those factors that add up to b. And again, that's because my a is 1, and when I combine the outside and inside terms, what I'm doing is I'm combining those two numbers that are at the end of those factors, that a and that c. And so we want to identify the pair of factors that add up to b. So let's say my factors are m and n. If they multiply to give me whatever a times c is, and they add up to whatever b is, then it can be factored in this form. So I made a mistake here, so I'm going to fix that right now. X plus m and x plus n. Okay. Like, for example, our equation earlier, 4x squared plus 20x minus 56. First, we factored out the 4. All right, so 1 times negative 14 is negative 14. So if I look at 14 by itself, its factors are 1 and 14, 2 and 7. Now remember, this 14 is negative. So really, when we pick a pair of those factors, one of those numbers in that pair has to be negative. Well, if I take negative 2 and 7, well, negative 2 times 7 is negative 14, but negative 2 plus 7 is positive 5. Those are the two numbers that I'm going to use. So I can go straight to the factoring stage. And when I do that, I end up with 4 times x minus 2 times x plus 7. And if you want to check your work, FOIL and distribute everything out, you should get your original problem, your original function. Now, let's suppose that my a is not positive or negative 1. The AC method can still work, but we have to add a few steps. And we're adding a process known as we're adding a process known as factoring by grouping, which is pretty much exactly what it sounds like. We're going to factor groups of terms here. So again, just like before, you want to factor out -1 only if a is less than is negative. Now, obviously, you want to try to factor out any other common factors, but these steps are assuming that you can't. So again, a times c, find the factors of the product add up to b. But then what we want to do is we want to rewrite that middle term as the sum of that pair of factors. That way we have 4 terms, and we can group the first 2 terms and the second 2 terms and factor each one of them out. And then once we do that, then we'll factor out the common factor from that result, and then that'll give us that should give us our factored form. Now this process here is the most similar to foiling in reverse. All right, so I'll show you with an example. This is actually what. All right, so this is 2x squared plus 11x plus 12. And I'm trying to factor that. Well, a times c, 2 times 12 is 24. Factors of 24 are 1 and 24, 2 and 12, 3 and 8, 4 and 6. Well, I know that 3 and 8 are going to give me 11. So now I'm going to rewrite 11x as the sum of those 2 terms, plus 3x plus 8x. Now, does it matter which term comes first? No, it doesn't. If this term was first and then this term was second, if these 2 terms were switched, I will still get the same answer. So it does not matter the order that you choose. So now here's one group, here's another group. So here, here each term has an x, so I'm going to take that out, 2x plus 3. Here, each of those terms is divisible by 4, so I'm going to take the 4 out. And I get 2x plus 3. Now, both of these terms have a common factor of 2x plus 3. So just like I pulled the common factor x out of here and wrote it like this, I'm going to do the same thing with 2x plus 3. There's a 2x plus 3 in both of these terms. I'm going to pull them out and factor it. 2x plus 3, and then multiply that by whatever's left, x plus 4. And there's my factored form. Now, again, why do we use a shorter process when a is 1? So the first terms when we multiply when foiling both have a coefficient of 1 and -1. So like, for example, with x squared, the only 2 factors involved are x in itself, okay? So when performing the outside and the inside steps of the foiling process, each product is the result of 1 times another number. So the 2 factors that add to give the middle term is more plausible. And again, of course, your first term is x squared, and its only meaningful factor is x. Thus, the 2 terms that make up the middle term will also be factors of the last term. Last thing I want to cover is special types of factoring. One involves something called a perfect square trinomial. Now, the reason why it's called a perfect square trinomial is it's a quadratic function that can be written as a perfect square when factored. So if m and n are real numbers, then let's say I have something that looks like this. Then I can factor it into m plus n squared. Same thing here, except now this time it's a minus. I get m minus n squared. All right, so keep in mind that there are 2 things that we have to look for. First, look at the ends. Are they perfect squares? Are they perfect squares? And if so, then is m times n times 2 give you that middle term? Okay, let's look at an example here. So let's factor 4x squared minus 24x plus 36. Well, 4 is a perfect square. X squared, of course, will always be a perfect square. So I can actually write this as 2x squared. The reason for that is, so 4 is 2 squared. If I multiply that by x squared, if I have the same exponent, there are rules for exponents that say that I can group them as 1 term squared. Okay, so that's why I can do that. 36 can be written as 6 squared. So now I need to look at the middle term. I'm not worried about this minus sign just yet. I just want to look at that 24x. Does 2 times 2x times 6 equal 24x? Well, 2 times 2 is 4. 4 times 6 is 24. Times x is 24x. So it does check out. This is a perfect square trinomial. So in this case, my m would be 2x. My n would be 6. Now, do I add or do I add? Do I add or do I subtract? Well, that all has to do with this first sign right here. That first sign determines whether or not you have a plus or a minus in your factored form. Here I have a minus, so that means I'm going to subtract. So my factored form ends up being 2x minus 6 squared. Okay. Now, I could have also factored out a 4 first and then done the same thing, but it wasn't really, but, you know, I just really wanted you guys to know just the basics of how to factor perfect square trinomials. But then we also have, now let's say I have my first term and my last term are perfect squares, but I don't have a middle term. Well, I can still factor. And that's what's called the difference of squares. Now, why is the difference of squares the way that it is? Well, if I FOIL this out, let's say I FOIL that out. M squared minus mn plus mn minus n squared. What happens here is the middle terms actually end up canceling out. And that's where I end up with this difference of squares. So again, if you're looking at difference of squares, or if you're looking at the factored form, you'll know that you get the difference of squares if the factors are almost exactly the same, except the signs are different. Okay. So let me just do a quick example. 25x squared minus 49. So no middle term. 25 is a perfect square. Obviously, x squared is a perfect square. So this is 5x squared. 49 is a perfect square, 7. So this can actually be factored to 5x plus 7, 5x minus 7 every time, as long as you have a perfect square minus a perfect square.